In calculus, sometimes you hit a problem that feels like a brick wall. It looks simple enough, but it just resists every standard method you throw at it. But what if I told you there's a powerful tool, a kind of mathematical skeleton key that can break these problems down? Let's see how it works. It's a feeling we've all had, right? You're following all the rules, you know the techniques, but some problems just don't give you a clean answer. It really feels like a dead end. But here's the cool thing about math. A dead end is almost always an invitation to just think differently. Okay, so meet the villain of our story today. This is the integral of the Gaussian function. You see it everywhere in statistics, but in calculus, it's kind of infamous because it has no elementary antiderivative. Now, all that means is you can't solve it using the normal rules you've learned. No power rule, no U substitution. It's the classic example of an impossible problem. And here's our hero, the Taylor series. The core idea is just brilliantly simple. What if you could take a really complicated function, like our e to the minus x squared, and rewrite it as something incredibly easy to work with, something like a polynomial. Yeah, an infinitely long polynomial, but still, just a polynomial. That's exactly what a Taylor series lets us do. So, let's see our hero in action, shall we? We're going to take that so-called unsolvable integral, and by using the power of an infinite series, we're actually going to find its solution. This is where the mathematical magic really begins to happen. Our whole strategy is basically a classic bait and switch. We start with a Taylor series we already know, the one for the basic function e to the power of u. You can see it over on the right. Now, it looks like an infinite sum, but each piece of it is just a simple power function. We're going to swap out the difficult function on the left for this much more manageable series on the right. Okay, so our first move is just a simple substitution. Our problem has an exponent of negative x squared, right? So everywhere we see a u in that general series for e to the u, we're just going to pop in negative x squared instead. It's a direct replacement, nothing fancy. And this is what we get. Our once terrifying function has now been rewritten as this infinite polynomial. Now, I know it might look a little complicated in that summation notation, but if you look at the individual terms, they're just simple powers of x, and those, we can totally handle those. And this, right here, is how we get around the whole problem. We couldn't integrate the original function, but integrating a polynomial? That's one of the easiest things to do in calculus. We just go down the line and apply the good old power rule to each term, one by one. And there it is, the solution. We've actually found the antiderivative as an infinite series. The unsolvable has been solved. Each term you see here was found by just integrating the matching term from the series we just built. Problem defeated. But the power of series isn't just for impossible integrals. Oh no. Let's see how we can use this exact same tool for another tricky part of calculus, limits. This method can help you completely sidestep complicated rules like L'Hopital's rule with some surprising elegance. All right, here's our next challenge. If you try to just plug in 0 for x, what do you get? 0 divided by 0, the classic indeterminate form. Now, you could use L'Hopital's rule, maybe even 3 times in a row, but man, that's a lot of tedious work, and there's so much room for error. There has to be a better way. And here is that better way. It's the same trick as before. We just perform a substitution. We know the Taylor series for sine of x, so we're just going to swap it right into the limit. This is that huge aha moment. We're changing the problem from a limit of a complex function to a limit of a simple polynomial. Now just watch what happens. It's so cool. The x at the very beginning of the sine series perfectly cancels out with the minus x that was already in the numerator. And that is not a coincidence. It's the beautiful underlying structure of the math just revealing itself. And what we're left with is a much, much simpler expression. So after that cancellation, our numerator starts with negative x cubed over 6, then plus x to the 5th over 120, and so on. Now we divide that whole thing by the x cubed in the denominator. The very first term just becomes negative 1/6. And all the other terms, they still have an x in them. So as x goes to 0, they all just vanish. The answer is simply negative 1/6. So clean, so fast, so elegant. Okay, so for our final application, let's bring this out of the world of theory and right into the palm of your hand. Have you ever actually wondered how your calculator computes values for functions like e to the x or sine? It's not magic, and it's not some giant lookup table. It's series. No, seriously, think about it. How does it do that? When you type in the square root of e, which is just e to the power of 0.5, what is the calculator actually doing inside its little processor? Well, it's performing a calculation based on the exact same principles we've been using this whole time. Your calculator takes the Taylor series for e to the x, and it just plugs in x equals zero point 0.5. Then it starts adding up the terms one by one. The first term is 1, the next is 0.5, the next is 0.125. See how quickly those terms are getting smaller? After just 4 simple additions, we already have a really good approximation. And here's the proof. Our estimate using just 4 terms is 1.6458. The actual value is 1.6487. I mean, look how incredibly close we are with so little work. Your calculator just adds a few more terms to get that insane precision you see on its screen. This is the power of series in action, and it's happening millions of times a day in devices all over the world. So let's just recap the superpowers we've unlocked today. Taylor series let us integrate functions that were basically unintegratable before. They let us blow through complex limits with simple algebra. And they give us the ability to approximate pretty much any function to whatever degree of precision we want. You know, this quote really says it all. This isn't just another technique you memorize for a test. It's a fundamental tool that just expands the entire landscape of problems we're capable of solving. It's like a bridge from the finite world of algebra to the infinite world of calculus. So I'll leave you with this thought. We've seen today how a tool like infinite series can take problems that people once thought were impossible and make them totally manageable. So the question isn't really what can be solved anymore. It's what new and interesting problems are you going to solve with this incredible power? Thanks for joining me for this explainer.